Okay, so I'm going to report on joint work with Anna Felikson, Anna Garcia, Elsener, and Pavel Tumarkin. And these are Frieze patterns associated to some surfaces known as the pair of pants. So I'll recall first the Frieze patterns introduced by Coxeter in the 1970s. And they are infinite arrays of numbers. You see an example in my slide. The first and the last rows consists of ones, and they satisfy a simple arithmetic rule whenever you have a diamond in the Frieze pattern, which is obtained by shifting the every successive row to the side a little bit. So the diamond rule says AD minus BC is equal to 1. Right? And so they're finite, and the width of the Frieze pattern is determined by number of non-trivial rows. And in this example, we have precisely 3. And Coxeter showed that such Frieze patterns are periodic with periods dividing the width plus 3. And they have a glide symmetry along the medium horizontal axis of symmetry of the pattern. And with that, we can simply consider some fundamental domain highlighted in blue in my slides here. And the interests of Frieze patterns in representation theory in general spark from cluster theory, and because of the connection that's given by Conway and Coxeter in 1973, that finite integral Frieze patterns with n, they are in one-to-one correspondence with triangulations of convex n plus 3. And this correspondence is quite simple and nice, and this is simply given by counting adjacent triangles on a triangulated polygon. In my example, this corresponds to a hexagon, and in each vertex, I count the number of adjacent triangles. Here I have 4, here I have precisely 1, and then 2, and then again 2, 2, and 1. And you see that gives this, oh, I have one more. Here, this non-trivial row of the Frieze, and then applying the downward rule, we can recover the rest. And there are some generalizations of this. I will briefly mention one. These are called infinite Friezes. They have a similar rule. Again, they are periodic. They have the diamond rule. The only difference is that the width is not finite. And you see an example here in my slide. And these were studied extensively by Bauer, Parsons, and Shabolt, and they show that such Friezes come from triangulations of analog. And the combinatorial rule is also very similar. If you take a triangulated analysis, you can again simply count the number of adjacent ideal triangles in this case. So here we have 5, here we have 4, and then 1, and then 2. And again, this gives me this non-trivial row of my Frieze, and starting with the ones and applying the diamond rule, we can recover the rest. And in such examples, those Friezes are always infinite. And there are other generalizations which I will not get into, but I would like to discuss a representation theoretic interpretation to these Frieze patterns. And I will really consider my example as being type A and a tilde, and I will build on it. So I'm actually thinking of a geometric picture in mind. But if we take a cluster category and a cluster tilting object on it, and for an indecomposable object in the cluster category, we can consider a specialized CC map. That's the Calderon-Chapaton map for type A, or cluster character by Palou in general. And this is simply given by, so the sum is all submodules of M. If the dimension vector is E, we consider the Euler-Poincare characteristic of the Courbet-Grassmannian of dimension E. And whenever we have an AR triangle in the cluster category of the form tau M, B, and M, applying this specialized CC map on it, we recovered the diamond rule in this setting. So we have SM as tau M minus SB is equal to 1. In particular, if our AR triangle is of this form, this precisely recovers the diamond rule we saw in finite and infinite cases. And the question I want to consider is, well, if I consider a general surface now and the associated cluster category, well, sum of Frieze's again can be given as a specialization of cluster tilting objects using the specialized CC map, but are they all? Are there any other Frieze patterns that don't come from this representation theoretic interpretation? And in general, for type A, this is the case. They all come from this representation theoretic interpretation, and so is for type A tilde. But again, I want to generalize this a little further. All right. Okay. I think I forgot to check my time, but it should be okay. So for that, I will first generalize the notion of Frieze patterns, and I'm going to use the one introduced by Fontaine and Plamondon in 2016. So for any curve Q, we'll consider the associated cluster algebra. A Frieze pattern or a general cluster Frieze is just going to be associated to this cluster algebra, is just going to be a ring homomorphism from the cluster algebra into the integers. And we'll consider such patterns positive, as it was the case in my earlier examples, if the image of this ring homomorphism falls into positive integers. And we are going to call them unitary if there is a cluster such that every cluster variable in this cluster is mapped to 1 under this map, lambda. Yeah. Okay, very good. With that definition in mind, let me consider Frieze's for a pair of pens. I sort of advertised that I was going to consider generalized surfaces, but I'll have to restrict myself to the pair of pens, which is the compact oriented surface with 3 boundary components, as you see in my example. And I will consider finitely many mark points on the boundary of my surface in the cluster setting, meaning I will have at least 1 mark point in each boundary component. And I'll consider the associated cluster algebra and lambda SM, a positive Frieze associated to this cluster algebra. And what we show together with Felikson, Garcia, Elsener, and Tumarkin is that all such Friezes are unitary. That means there is a cluster for which the image of cluster variables on this cluster is always 1. And as a corollary, we can say that such Frieze patterns always can be recovered by a specialization of this CC map. And I will finish off with one remark why we actually had to restrict ourselves in such surfaces. So it's just pair of pens, but not general unpunctured surfaces. So what we do in the proof is that we associate a hyperbolic structure to this surface, which we can do in general, but then we do cutting along an arc that brings us to smaller surfaces, and in which we do quite a bit of case analysis that we are able to do if we are on a pair of pens. But for general surfaces, there is one case that we are not able to solve. So with that, I will conclude my talk. Thank you for your attention.